Okay,
Hey
is
pre-calculus
this
friends, here we
happening?
are in chapter 2
Apparently it
and
is, where
we
you see
are
my
going to
entire
start
screen.
talking about solving systems of
How am I supposed
equations
to know?
into variables. So our vocabulary for this section is as follows. We're going to be talking about systems of equations. And really, if I'll be honest, we should probably put linear here because this section will really cover systems of linear equations, equations that we get aligned when we draw them. So what does that look like? Here we go. A system of linear equations is when you have two or more equations, linear, that basically are dealing with the variables x and y. Sometimes they might have just an x and or a y. And what we want to do is find a solution, some xy point, that can work for both of these. And so that gets us to the next vocabulary term, solution. So a solution is just the value or values that works in each of these equations. And so now we need to consider, what do these systems of equations look like when we actually are graphing? And so, really, what we have are three situations that you need to consider. And those situations are basically when I graph these two lines, a couple things can happen. So, one thing that might happen, which is great, is we graph the two lines and we get indeed a solution. And that solution would be here. That would be the xy point that satisfies both of the equations. And that would be lovely. Another situation we can get is where one line is actually, instead of crossing another one, parallel to the other one. So there is no solution here. And sometimes we even get this strange thing where one line is exactly the same as the other. And so we have kind of a situation where we've got these overlapping lines. And so that's a situation that has a distinct, well, actually, it has infinitely many solutions, but obviously a distinct look. So let's talk about what they are called. So these next four vocabulary terms are going to refer to the situations that we see here. And so when we look at them, we want to be able to use the right terminology for each. So this first one, is considered consistent. Now, the consistent idea is that there is an answer. There is at least one answer. And so over here, this overlapping situation is also considered consistent because there are infinitely many solutions. Every point is going to be a solution for both of these, for this particular system of linear equations, right? So I'm going to highlight that. And then the next term is independent, and we know what independent means. These two lines are different, whereas these two aren't. So this is considered an independent situation. This is independent, all right? And so now that we have that down, we need to see where dependent comes from. And I think you probably figured it out. This is dependent because both these two lines are not independent, they are dependent on one another. And then finally, the term inconsistent will go here because it is, remember, consistent meant a solution, so inconsistent means no solution. No solution is present here. And so I'll highlight those accordingly, and we'll continue with our other vocabulary words. So we've got two here. Two more left, but I'm going to add a third one, and that's using the graphing method to solve these guys. And you probably intuited or have seen it before just from what we did here. You're going to graph two lines and you're going to figure out where the solution is. So we've got three situations: elimination, substitution, and graphing method, and we're going to demonstrate them in the next few examples. So instead of giving you a quick demonstration here, I'm going to actually wait for the next couple of examples to do so. So let's check out example one, where we are going to solve this system by graphing. So as I indicated before, the graphing method requires that we graph each of the linear equations. And so, the best way for us to actually graph a linear equation is to probably put it in y equals mx plus b form. When I do that with this one, the y stays on the left side, the x moves over, and this is the equation that we have. And when I do it for the one above, it's a little bit trickier, but the y will remain here. We'll move the negative 3x over to the other side, but then we'll be dividing everything by negative 2. So we get a positive 3 halves x minus 6. And so, oh, not minus 6. If I'm dividing it by negative 2, it actually becomes a positive 3. Thank you for the correction. Okay, so I'm going to graph each of these and we're going to see where it leads us to. So then I've already done the pink one, so I'm going to go and do the blue equation where my negative 2 is my x-intercept, my y-intercept rather, and I rise one, go back one, up one, go back one. And you can see that we found the place of intersection, even if my line doesn't look that great. We'll do something like that. And you see that we have our solution. So our solution is here at negative 2, at negative 2, 0. That's the ordered pair. And we can plug that right back into the equation. And we'll see when we do that, that we actually have a solution. It works in both equations. You'll see on page, I think it's 68 in your textbook, this picture, which is a lot like what we talked about in the beginning, a little bit more description of what the slopes would be like in comparison to each other. But this is going to be a handy thing for you later on. Okay, so now we're going to deal with the elimination method. And the elimination method basically is this. You pick a variable, it has to be lined up perfectly. So what I mean is, like, if this, you notice this is in standard form, ax plus by equals c, then the bottom one has to be in standard form. So the variables, the operation sign, the equal sign, and the constant all need to be lined up. And then you decide what variable you want to get rid of. I'm deciding for y. I'm going to get rid of the y variable. And we do this by multiplying the top and bottom by a number, the top equation and the bottom equation, by a number that is going to turn the coefficients into, what do we call them? Additive inverses. So I'm looking at these guys, the signs are already different. So I'm like, ooh, I can make this first equation have this y have a coefficient of 10 by multiplying this first equation by 5. Let me get all this excess stuff out of here for you guys. And boom. So I can get rid of the y variable by multiplying the first equation by 5, and I can get rid of the y variable, or make the coefficient negative 10 in the second equation by multiplying this equation, both sides of course, by 2, because we know what we do to one side, we do to the other, and it maintains equality. So I'm going to rock a distributive property here, and I get a 7.5x when I multiply 5 times 1.5 plus 10y, which was my goal, is equal to 100. And this second equation becomes 5x minus 10y is equal to negative 50. And what I'm going to do now seems a little weird, but I'm going to add both of these equations together. You get it. If 5 equals 5 and 7 equals 7, right? If I add those two together, it should be 12 equals 12 makes sense. If I add two things that are equal, then the result will be equal. So same thing here, except when I do this, I add straight down and I get 12.5x. These guys cancel out, and now I've got a 50 over here. And now this has eliminating one variable means I can solve this much easier. I know I'm going to divide both sides by 12.5. When I do that, I am left with x equaling 4. So if x equals 4, I'm not done because I still need to get my y term. Remember, the solutions to linear equations are generally going to be a point, so it's an ordered pair. I'm looking for the complement to 4, meaning when I plug 4 back into the equation, I want to know what the y value is. So I'm just going to take the first equation, substitute that 4 right in there, and now I'm going to solve for y. This is going to give me 6, so 6 plus 2y is equal to 20. 2y has to be equal to 14 by subtracting 6 on both sides, and y is equal to 7. So the solution here is 4, 7. And now we're going to take a look at the substitution method. So the substitution method is probably the one we learned first in terms of the algebraic ways of manipulating these types of problems. And what we're going to do is take one of the equations, it really doesn't matter which one, and figure out a variable that you want to isolate. X is looking like it's practically alone here. So in the second equation, so I'm looking at that second equation, I'm thinking that's where I'm going to go. So I'm going to isolate the x by simply moving the y to the other side, and I get x is equal to y plus 2. So this I'm going to substitute in here for this x equation there, or that x variable there. So here's what I'm doing. I'm going to substitute that. So you'll see it here. Watch the rewrite. I have 2 times not x, but y plus 2 plus 3y which is equal to 8. And notice now I only have one variable here, which is exciting because I know how to solve an equation when there's one variable. So I have 2y plus 4 plus 3y is equal to 8. Joining some like terms together, I end up with 5y is equal to positive 4. And that positive 4, let me get rid of that, make it look better. Positive 4 comes from subtracting 4 from both sides, right? And so right now you're probably shaking and you're like, wait a minute, it's a fraction, nobody likes them. But you know what, we're big boys, we're big girls, we can actually figure out fractions. So yes, it is 4/5. It is true, it is right, it is just. But now, of course, we need to figure out the x value. Lucky for us, we have it pretty much handled as we've already solved for x. We're going to put 4/5 in for y, add that 2, and we can write our answer in a number of ways. X is equal to 2 and 4/5. If you're digging the improper fraction mode, x could be equal to 2 times 5 is 10 plus 4, 14 over 5. And if you're a decimal friend, then you've got 2.8 that you're working with. So I'm going to write this as an ordered pair. I'm going to rock out with the 14/5 and 4/5 as a solution here. I'm going to ask that you take a moment to read this. Pause me if you must. Okay, hopefully you did that. And what we're looking at is Madison's situation. She has decided to lease a car for 2 years, and she's got two choices. One, the cost for her will end up being $200 down plus $326 per month, and we'll use X for months or M. M is nice. We'll use M for months, but it would usually be the X variable that we'd call that independent variable, and then C being the dependent as in Y. And then for her other opportunities, the cost could end up being initially $1,600 plus $226 per month. And so we are asked to do two things. One, what is the break-even point? What is the time when both of these opportunities will, it wouldn't matter which opportunity you choose because the value would be exactly the same. The cost to her would be the same. And then, so that's the break-even point. And then the other one is how much, which is the better lease if she has $200 or $1,600, either one is fine for her. And I think the best way for us to do this is for me to go to Desmos instead of you checking out my graphing skills by hand. So I'm over here in Desmos. I put the two equations in and my graph looks ridiculous. And so you want to make sure that you are looking at a graph that makes sense to you. These are the lines, but look at where we are. We're at, 0 to 2, 3, all the way up to 10 on the x-axis, and look at our y-axis. And we're talking big money here. We're talking initial price of $1,600. So I'm just going to do this just in case you haven't been able to adjust your Desmos screen. So I'm just going to start at 0 months, and since we're going out to like 24 months because it's a 2-year lease, let me go out to 25 or 30. Let's do 25. And then so that's my X, and so my Y. I'm dealing with some big money here. So I'm going to start off at 0, but I'm going to make sure and go up to maybe 10,000 because I don't know how much money this is going to cost Madison in the long run. So now that I've chosen a reasonable screen for my graph, you can now see the line, and you can see both lines. So the red line refers to the situation where she puts down $200 initially, and so far so good. As long as if she could break her contract and get out of it, it seems like choosing this is pretty good until the break-even point. And I don't really think you can break a lease contract. I think there's all kinds of penalties, so that's not really an option. But the break-even point is at 14 months. No matter which choice she chooses, she will have already invested $4,764 into the account. And so the next thing we want to do is consider, so the break-even point is at 14, is at month 14 with that amount. The next thing we want to do is think about how much she's going to pay overall, and that will be calculated by considering what's happening at the 24th month. And so I'm going to put in the vertical equation, the vertical line at x equals 24. And you can see over here at the side of your screen, let me zoom out a bit, you can see that it's quite a difference. It's about $1,000 difference between the two options. So if she chooses the one that initially cost her $1,600, she will end up saving $1,000 by the time she reaches the end of the lease, as opposed to the cheaper one, the initial one that's cheaper, then she would pay $1,000 more. All right. I hope that made sense to you guys. And I hope that was really our last example. So I hope that made sense. I hope that the exercises make sense to you and that if you have any questions, you'll feel free to contact me and let me know how I can help. All right. Please take care. Bye bye.